Good morning students. Today we will discuss about Davisson and Germer experiment or experimental verification of matter waves. This is the experiment which proves particle exhibits wave nature. We have seen in the last classes that according to de Broglie, particle exhibits wave nature, but it was not experimentally proved by de Broglie. This was experimentally proved by Davisson and Germer. The basis of this experiment is, see here, in order to understand the basis of the experiment, first we should learn about Bragg's law. We should have brief introduction about Bragg's law. Now, if we see Bragg's law, we have studied Bragg's law. We know Bragg's equation 2d sine theta is equal to n lambda. See here, these are the crystal planes. These are the crystal planes. And when X-rays falls on crystal planes, they get diffracted at an angle theta. The distance between two planes is d. The distance between two planes is d. D is called as interplanar spacing. D is called as interplanar spacing. And theta is the angle of diffraction. Angle of diffraction means this is the angle of diffraction. Next, n represents order of diffraction. N represents order of diffraction. Okay, this is about Bragg's equation. 2d sine theta is equal to n lambda. Here, why only X-rays are made to fall on crystal planes? Why not other rays on the crystal planes? Okay, in order to understand this, first we need to understand about diffraction. So what is meant by diffraction? The bending of light around the corners of an obstacle. So if I place obstacle in place of light, means when light is made to fall on the crystal obstacle, what happens? It bends. It bends and it forms the geometrical shadow of this object. This is called as diffraction. Now, what is the condition to get diffraction? The wavelength of source must be comparable to size of the obstacle. The wavelength of this light should match with the size of this obstacle. Then only diffraction occurs. So see here why only X-rays are made to fall on crystal planes means the wavelength of X-rays is 1 angstrom. The wavelength of X-rays is 1 to 2 angstroms. The size of the crystal plane is 2 to 3 angstroms. So here wavelength of this X-rays matches with interplanar spacing, size of the obstacle. That's why X-rays are made to fall on crystal planes. Then only they get diffracted. If I use visible light is of wavelength 5000 angstroms, 5000 to 6000 angstroms. But if the size of the obstacle is 2 to 3 angstroms, does diffraction occurs? No, because the wavelength doesn't matches with size of the obstacle. Okay, so here X-rays are made to fall on crystal planes. So this is about Bragg's law. But when we come to Davisson and Germer experiment, instead of X-rays, they have considered electrons. Instead of X-rays, they have considered electrons. Why only electrons? Why only electrons means electron wavelength is similarly equal to X-ray wavelength. X-rays wavelength is 1 angstrom to 2 angstroms. So electron wavelength also lies between 1 angstroms to 2 angstroms. So here instead of X-rays, Davisson and Germer considered electrons. So electrons are made to fall on crystal planes instead of X-rays. Okay. Now we'll go to our original topic. So see here, the basis of this experiment is wavelength of electron is order of X-rays. Here wavelength of an electron is order of X-rays. So what happens here, instead of X-rays we'll use electrons. So a beam of electrons must show diffraction effects from a crystal like X-rays. So when X-rays falls on crystal planes, how it gets diffracted, like that only when electrons falls on crystal planes, they also should diffract. So if this diffraction wavelength means, what is the diffraction wavelength? 2d sine theta is equal to n lambda. 2d sine theta is equal to n lambda. If this wavelength, if this diffraction wavelength coincides with de Broglie's wavelength, what is the de Broglie's wavelength for electrons? Lambda is equal to 12.26 by root V angstroms. So, if this diffracted wavelength 2d sine theta is equal to n lambda, that is lambda is equal to 2d sine theta by n. If this coincides with de Broglie's wavelength lambda is equal to 12.26 by root V angstroms, then this experiment will be proved. Okay. So, next we'll move for experimental arrangement. Now, the experimental arrangement is shown in figure. So, see here we can see the experimental arrangement. So, this is the filament F. So, F represents hot tungsten filament. Hot tungsten filament. P represents plate. So, P is the plate. Next, see here, now here hot tungsten filament. From the hot tungsten filament means when voltage is applied, between filament F and plate P. Filament means nothing but bulb. In the bulb, filament. So when you give voltage, what happens? Current flows through the bulb. So the light will be glowing. So means electrons are moving. So see here, hot tungsten filament produces highly accelerated electrons. These electrons, see here, these electrons are made to pass through pinhole O. So these highly accelerated electrons are made to pass through pinhole O, and they are made to strike nickel crystal. These electrons are made to strike nickel crystal. How this electron beam and nickel crystal are? So this nickel crystal is placed perpendicular to the beam of electrons. So when this electron beam strikes nickel crystal, what happens? They get diffracted. So see here, when this beam of electrons strikes nickel crystal, it gets diffracted at an angle phi. It's get diffracted at an angle phi. So this diffraction pattern is recorded. See here, these diffracted electrons are collected at detector D. So this is detector. It is collected at detector D. Detector D is mounted such that it can move throughout the circular scale. So this detector D can rotate throughout the circular scale. This circular scale will be up to 360 degrees. So I can place this detector at 10 degrees, 20 degrees, 30 degrees, 40 degrees. Like that I can record up to 360 degrees. Now, how many electrons are collected? Here electrons are collected at the detector. How many electrons are collected? That intensity is given by galvanometer deflection. So G represents galvanometer. So that intensity is given by galvanometer deflection. Okay. So how many electrons are collected? That count will not be given. Its intensity will be given. Means if more electrons are collected, more deflection in the galvanometer. If less electrons are collected, less deflection in the galvanometer. That can be given. So see here, once we'll see again, this highly accelerated electron, when voltage is applied between filament F and plate P, highly accelerated electrons strike nickel crystal which is placed perpendicular to electron beam. and they get diffracted at an angle phi. These diffracted electrons are collected by detector D, which is mounted such that it can move throughout the circular scale. Here, the intensity of the collected electrons is given by galvanometer deflection. Means intensity of collected electrons is directly proportional to galvanometer deflection. So that related notes you can see here. That related notes you can see here. Whatever we have explained, that is given in the notes. So the deflection in the galvanometer is directly proportional to intensity of beam emitting the detector. So this is about the experimental arrangement. So in the next part, we'll discuss about theory. Thank you.